now let's constrain the pressure of a system. So we're going to do constant pressure. And I said this one was a little more complicated. It both is and is not more complicated. So at constant pressure, the delta E reaction still has contributions from heat and work, right? We haven't constricted the volume, so we're still going to have a work component. I mean, for heat, if the only thing that you could restrict that would make the heat drop out would be the temperature. So that's also not helpful here. So, right, all of those things are still there. However, we usually don't care about the work. Someone probably cares about the work, but as chemists, the things that we're looking at, the information that we want to use, the work doesn't really matter. And even better, the contribution for the work is often very small. So, compared to the heat that's being transferred, the amount of work that is done is really small for the systems that we tend to study. Now, why this happens, right? If you're thinking about doing chemistry at constant pressure, that sounds like a weird set of conditions, but those are the normal conditions under which we do everything, right? The pressure is 1 atmosphere approximately on Earth in the inhabitable portions. It's always constant pressure. Pretty much everything we do is at constant pressure. So that any flask that you're doing a reaction in, if it's open to the room that you're doing chemistry in, if it's open to the fume hood in the lab room, well, that fume hood, it's open to the room that you're in. The room is open to the building, even if the door's closed, right? There are gaps, there's ventilation. The building is open to the outside. So when we're looking at a change in volume, right, it's like the volume, the initial volume of the universe minus the final volume of the universe, or even the room, it's enormous. The delta V is really, really tiny when we're doing work at constant pressure. So what we do, what chemists have done, is created a term called enthalpy to describe what the heat at constant pressure is. So we define enthalpy as energy plus pressure times volume. Thankfully, enthalpy is a state function, so just final minus initial is all we need for it. So we can say that delta H is equal to delta E plus P delta V. I'm like, okay, well, delta E is Q plus W plus P delta V is the opposite of work because work was negative P delta V. So heat plus work minus work, the enthalpy is equal to the heat at constant pressure. And we have written this as a new term. We have redefined it because technically and officially, we're not getting rid of the work. However, because the work is small, it's not going to have an effect on the answers that we get and the usability of the information that we get. So delta H, if you have an endothermic reaction, delta H is positive. The reaction absorbs heat, which, right, you can reason through from Q because this would mean that the temperature is increasing. So your delta T is positive, so your delta H is positive. An exothermic reaction has a negative delta H and gives off heat. Delta H is an extensive property. So just like what we were looking at with the combustion of sucrose, This also depends on the amount reacted, which, right, you kind of know from the MC delta T in the Q calculation. So this delta H reaction, we will write it per mole or we will write it in reference to a reaction. Usually when you see it reported, it's in this in reference to a reaction way. So combustion of C3H8, I have my balanced reaction, and then I have delta H reaction equals negative 2044 kilojoules. So what this means is this reaction gives off negative 2044 kilojoules for every 1 mole of C3H8 that reacts, which means with a reaction and a delta H value next to it, you can use this as a conversion factor. Now, we're going to use the conversion factor that I have set up here, but this is relative to the entire reaction. So you will give off 2044 kilojoules of heat for every 5 moles of O2 that react, or for every 3 moles of CO2 that are produced, and so on. So in the question, how much heat is given off when 0.248 moles of C3H8 is burned? We know how many moles of C3H8 we're using, and we know how much heat is given off per mole. So we can use that information to say that we would expect negative 506.9 kilojoules of heat to be given off.